Hello, everyone. We're back, back and better than ever. Today is day 7 of the daily coding challenge, so that's 1 week. Today is January 22nd, 2025 at 2:16 p.m. So today is my first day of class, even though I don't have any classes today. So we'll see how this challenge goes, how it transitions into schoolwork. But here we are looking at day 16 of Advent of Code. Okay, so let's read it. So it's time again for the Reindeer Olympics. This year, the big event is the Reindeer Maze, where the reindeer compete for the lowest score. You and the historians arrive to search for the chief right as the event is about to start. It wouldn't hurt to watch a little. The reindeer start on the start tile marked S, facing east, and need to reach the end tile. Okay, every time they move, they get 1 point. They can't go into a wall. They can rotate clockwise or counterclockwise 90 degrees, increasing their score by 1,000 points. Oh, we want the lowest score. Okay, I was confused. To figure out the best place to start or sit, you start by grabbing a map. There are many paths, but taking any one of the best paths would incur a score of only okay, note that the path shown above includes one 90-degree turn as the very first move. Okay, because it starts east. I mean, what I could do, I think, is just kind of there's probably a better way to do this, but I could just brute force it, I think. And basically try every path. I wonder if there's some sort of heuristic we can make that's where we can try to minimize the score. So an idea I have is like always go forward if you can and only turn if you have to. I think I'll just try writing the brute force for this. I think that would be a good accomplishment for me. If I could just brute force this, I think that would be a good step. These problems definitely are getting a lot harder. But I'm pretty sure this is just a basic. You can just do a DFS. And then, well, okay, so the problem is you have to keep track of which way you're facing. And you can only go perpendicular to where you're facing, so you can't go backwards. So for instance, let's say we have say like this is a path that leads to the answer. Okay, so we start here. We go, let's assume we start up. So we go, okay, so we'll have a stack. Okay, so we start here facing that way. So our stack is, and then if we just give these coordinates, let's say 0, 1, 2, 3, 1, 2, 3, 4. Okay, so our stack would be, so first we explore ahead of us, east, and this is a wall. So think of these as hashtags, etc. So this is a wall, so we don't add it to the stack. Then we search to the right and left. So to the right is also a wall, so we don't do anything. And then we search to the left. So we have to maybe have a dictionary that's like turn left and turn right, which the key is your current position and the value is what your new direction would be or something. Okay, so then we see this one, so we add it to the stack. So 2, 0. Okay, so then it explored everything, all its neighbors. So we add, I don't know if we add it to visited. I mean, we must. I guess I'll just say that's visited now. Okay, so then we pop from the stack, and now we explore all the neighbors of, this position 2, 0. So pop that. So first we start, so we'll always just go, I guess, straight left and then right. Even though I did it the other way in this example. Yes, we'll go straight left, right. I don't think there's any indication of, well, we could maybe use something similar to the A star, kinda, where like, maybe we could just quickly calculate the distance. Like if we have to choose between left and right, maybe we can say, if the distance between, like, so, okay, so just to illustrate this point here. So if we have, so this is a wall, let's say, and then let's say E is over here. There's maze that way and maze that way. We can say, well, we'll pick this one because the distance between this tile and E is less than the distance between this tile and E. So we can use, like, even though this might be the path, maybe on aggregate, we should pick the direction that is closer to E. And then another example would be, so if we are facing that way, let's say E is up here. And we could either go left or right, so this is a wall. So we'd say that this point, so if they're both not walls, then we can say that this point is closer to this point. And how you would define closeness, we could just say like the total of y. I mean, we need the distance formula. Isn't it like, I'm just going to look up the distance formula for a second. Okay, so it's the distance is x squared minus x1 squared plus, okay, y2 minus y1 squared. Okay, so maybe we can just calculate this, because that's linear, for both the positions, and then choose the one with the lowest distance. just as maybe a slight optimization. Okay. And then obviously we'll just keep track of our points for each path. Oh, okay. So maybe if we need the position and we also need the score at that point. So that way when we go back to it, we know the score we were at. Yeah, so maybe we could just do like for every position we'll do X, Y, and then score or something like that. Okay, so let's go with that for now. So let's read from the file. All right, and we'll start with the small maze. Okay, so let's see. Typo? Yeah, typo. Reindeer maze. Okay, there we go. Okay, so first, we want to construct maze and also extract start and end positions. So to do that, we'll say for line in f dot read lines. So we'll say maze. It's an empty list. So we want it to look like, yeah, okay. I think I don't have to over explain that. So row is empty list. For points in line, or yeah, for point in line dot strip, row dot append point. So here we want column to go by 1, and here we want okay, so let's just print row num, column num, make sure everything's good there. Okay, 14 by 14. Well, 0 to 14. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, looks good. So we want to check if points equals an S, start location. I guess we could say start equals row num, column num. elif point equals e, end equals row num, column num. Okay, and then so that will extract those. So if I print start end, and then I also want to print maze. So maze is empty. Okay, perfect. There we go. Great. All right, so now what we want to do is, I guess, traverse maze. Okay, so stack will be equal to, so we'll do tuple of start 0, start 1, and 0, which is score. Okay, so while stack current equals stack.pop. Then we want to explore okay, let me do this real quick. What was the formula again? Square root of two things that are squared, or plus here. And then we want x2 minus x1, so we'll say end row minus row, then end column minus column. Okay. So let me just test that function. So let's say from the point 0, 0 to 2, 2. Okay, I have no idea if that's true or not. So let's say, so this should give us 2. All right. Looks like it's working. Not muted, good. All right, so this will return a float, which is the distance. All right, so, and then we also need visited. So that'll be a set of points. And we also need, so I guess like, so we could have a function called point at left, or point at direction, which takes in a direction. Well, I guess it would take in So taking the direction, so target direction. Well, I guess we would just need, well, we need the point and we need current direction. We need target direction. And is that it? So current direction. So direction will be defined as so it'll either be -1, 0 for up, 0, 1 for right, 1, 0 for down, and 0, -1 for right, left. So current direction is equal to east, which is 0, 1. So I'm thinking about how to do like turning. So I'm thinking of having maybe just 2 dictionaries called turn left and turn right. And then it will be, so left, for instance, if the key will be, it's basically a function we're going to use as a function, but so the key will be your current direction. So if you're facing, so let's just copy that. So the key will be a tuple of your current direction, and its value will be your direction if you turn left. And I don't know if there's a math cheat code that we can use. So here, if you're facing up and you go left, that would give you left. They're actually, and if you're facing, well, this is right actually. So you'd go left. If you're facing, well, I think I have another idea actually. So directions. So if we make it a list of tuples going clockwise, starting from up. So up, right, down, and left. So if we have those like that. So if you're at any point, you want to just move over 1. So if you, all right, let's say you're looking to the right. If you want to turn left, you go to this one. And if you want to turn right, you go to this one. So first we need to identify like the index of my direction. I guess I could say, I could just make that a dictionary. Okay, so for instance, you would take in current direction. So direction to index of current direction. So that gives us which one we are, and then if we want to, so if target direction, so this would be if target direction equals left, because we can only go left or right. I guess we could go straight. I guess like clockwise. Forward. So we will pass one of these three directions. So if we're going forward, then we don't do anything. So I could just say like, just do nothing for now. We will have to do some code there. If we're going clockwise, that's to the right. So we want to say is equal to directions at direction index plus 1. Otherwise, minus 1. Okay, so then are we just trying to get the coordinates? I guess we have to think about. Yeah, we could just get so next move coordinates is equal to so the next row is going to be equal to, let's just say so our next R will be it's equal to our current R plus new direction of 0. And then this equals our current column plus new direction of 1. Okay, so essentially I want, so this function returns a coordinate based on current position, direction, and the direction you want to go. Okay, so let's test it. So let's say I'm at point 0, 0, and I'm currently going up. And I want to go clockwise. So this will give me the 0.10, I believe, which I don't think is actually what we want, but I can use that 0, 1. Yeah, that's correct. So what if we're at 0.45 going to the right, and I want to turn clockwise? This will give me the 0.55. Okay, I don't think I need, because this essentially turns and gets me the point, which could be useful for checking walls. So that way I don't have to turn, check a forward, unturn. All right. Okay, so current equals stack.pop. So we want to check all three. So for neighbor and forward, so for each of those, we want to call get chords at direction. So we'll give it RC as our current, and then our direction. Let's say current direction. And our target direction, which is possible direction. Okay, let's see what this does. Okay, 13.1 and 1.13. So none. So forward east. Oh, we just returned, that's why. So we're not actually updating our position or anything. So this is just getting the coordinate forward, which is, it says 13.2. Yeah, let me just do that. No, that doesn't work. Well, if we imagine this is 0 and this is 14, so 13.2 would be the one forward, and then clockwise would be 14, 1, and then counterclockwise would be 12, 1. Okay, sweet. Points ahead. So if points ahead is a wall, then don't do anything. If it's a dot, so if it's a dot, then we want to append. We will go there. And score. Well, I guess what we want to say is like, if possible direction equals clockwise or possible direction. So if we've turned, then we want score to go up by 1,000. Otherwise, score should go up by 1. And we also need to add stuff to visited. So after we go through all of it, then we'll say visited.append or visited.add. Still not muted. All right, visited.add. We have to also check if it's not in visited. So we want to check if visited.add. So just the coordinate, I guess. So it would be, so visited will be a set of tuple positions. Should I also keep track of the score? I'm wondering, like, if we get to a point that we've already been to, but the score is less, then maybe we should just discard this line. For now, I'll just add the position, but I'll say current. Okay, so I have to go somewhere, so I'll be back to finish this later. But yeah, I think we got a lot done here, actually. So, all right, I'll be back. All right, everyone, I'm back. So it's been about a half hour, so let me try to remember where I was at. So let me try first before I implement like any memory about like places we've already been before. Well, I'm not sure if this. Basically, this just doesn't visit any place we've already been. Which could be incorrect, because if I have a path, for instance, let's say that my first path is like that. Okay, so we mark all those off as visited. And then eventually down the stack we get to this point. And it goes here. then we wouldn't be able to find the end with the cheaper solution. So DFS will just get us a solution, but we need to find the lowest score. So I think instead what we should do actually is keep track of every point that we visit. And instead of just saying we can't visit it again, only allow us to visit it again if the new score that we've reached is lower than the previous score that was at that point. So let's say with the red track, when we get to this point, we're at like 5K score. And then when we visit it again through here, we're at 2K score. So we can overwrite this score. So like as long as, so you can overwrite a point as long as the, as long as the score that we currently have is less than that score. So the problem with that is that we would need, so maybe instead of a visited set, well, maybe we could have a visited set of all the things that we visited. But it'll have a third element, which is the score. So instead of checking if it's unvisited, check if the score at this point is lower than the score what we've reached. But there is a caveat to this as well. So it has to be like for instance, facing. So let's say like in this example here, right, we approach it from two different directions. So let's say we do the red path first, and we reach the red path here with a score of 5,500. Okay, and here we reach it with 6,000. So this path is actually fine. Because this path has to turn. So there's two solutions to this. Visited set also will include the direction when we got there. So if we've visited that, but from a different direction, we can visit it again from the new direction. So like direction specific memoization. And then our second solution would be like minus 1,000 or so. So that way, so it has to be within 1,000 points because like if we're going here, so if this is 1 point and then, okay, so let's say we have yellow and blue. Those are two paths, and then this is 1 point. So if the yellow got here 1,000, or yeah, it would be like 1,000 or less than the blue, then we'll count it. So if the blue, so count yellow if yellow is 1,000 to negative infinity more than blue. So in other words, yeah, okay, I think I get it. So that's one thing. Of course, the problem with this is that if you come from the same direction and one of these is 1,000 behind, you'll be able to visit it again, which is not good. So I think we'll just do this. So in visited will also include the direction that we came from. So current direction. Okay, so in the stack, we should also have current direction, which in this case is east. Okay, so I'm going to change these a little bit. Okay, so in the stack is a tuple of 4 elements. Okay, so in the stack is a tuple of 4 elements. So we have start row, or I guess it would just be like row, column, current direction, and score at that point. Okay, so that's good. So when we append to the stack, we want here to be our current direction. So in this case, if we turn, we also want to change current direction to okay, so we'll report the point and the new direction here. And then when we call this function, we will also take points ahead and current direction. So this is like, so it'll give us the point and the direction that we're now facing. So if we go straight, for instance, it won't change current direction. Okay. And now I guess we'd want to add visited. I guess we could add it here. So it would be, we want to add the new position. Or no, we want to add what we just did. So we would just add current then. And then, okay. So let's see what errors I get. Score. Okay, so we also want here current direction and score like that. Too many values to unpack. Get chords that direction. I thought it returns 3. Okay. So it exits. I have no idea what that did. So I guess I could print visited at the end and see. I don't expect this to work. Okay, so it only does it for one element in the stack. So let me print visited after that. So it should just be. Well, that doesn't make sense, does it? Okay, so let's. And we don't want to see if it's invisited. Okay, so if it's a wall, then just jump out. So if point ahead, well, we actually want maze of point ahead, right? Because point ahead is just a coordinate. So yeah, if all right. So we're actually gonna do it how it was. Okay, and then we'll take point ahead x, or sorry, point ahead row and point ahead column. So if maze of point ahead row and point ahead column equals a wall, then we will continue to the next direction. Okay, similarly, if Okay, so we want to check if, so it's a set of tuples. So if point ahead row, point ahead column, maybe we want a dictionary actually. So visited will instead be a dictionary. So we want these three elements to be direction, to be the key, and the value to be, okay, to be the min score at point, which also will serve. So min score at point, which will be a dictionary. Then here we'll say if min score at points. No, if point ahead just fix that up. Okay, so if point ahead row, point ahead column, and current direction, so if that tuple is in min score at points, so if it's in it, then, okay, so if it's not in it, then we want to say min score at points of that location equals score. Otherwise, if it's in that, then we say this equals the minimum of itself. All right, I gotta use a variable here. Let's say okay, if points and it's the minimum of itself and score. So whichever is lower. Otherwise, just make it score. Okay, that makes sense. Okay, this makes sense. So it's a dictionary that takes the point in the direction and outputs the score. So update, adjust memory to include lowest score seen so far. Still not muted. Okay. So point and direction is equal to that. Well, we don't have point ahead R yet. So I don't think we need points ahead. So this we probably don't need. Okay, so if point and direction, okay, so this part, simple enough. So if it's a dot, then just for clarity, I'll do that. Okay, so we add to the stack our starting position, current direction, and a score of 0. And then we create min score at point, which is empty dictionary. Okay. So we want to, so we have current, and then we check the forward position, clockwise, and counterclockwise position, which are these. So if it's a wall, then you do nothing. And if it is a period, then you basically want to add it to the stack with the score that it would have. And you want to change also the direction that you're facing. So this should not be, it shouldn't just be current direction. Okay, but this returns a new direction. Okay. So this would be new direction instead. Yeah, so the current direction just gives you the new direction basically, and that's okay, that works. So we append the new points and the new direction. And then the score. So if we turned, yeah, so if we're still in this point and we went clockwise or counterclockwise, then the score should go up by 100. Okay, so now my problem is, when do we adjust this? So I think what we want to do is after, so we explore all the neighbors and then say, well, like we can probably just add this up there. But we also need to check somewhere too, if any of the neighbors, if we've been there before with a lower score, then we don't want to check it. So I think that's where we do this. So don't add neighbor to stack if wall, and then don't add neighbor to stack if we have, I guess, if visited with a lower score. So we could say here, if this new point and direction is already in it, and the score, well, I guess maybe we should check it here, because this is when the score actually gets added, right? Well, it depends on when we're adding it to the stack or to the memory. So I'm thinking we probably want to right when you get somewhere. So if we have like this, so right when you get somewhere, you should probably instantly say, you should instantly go to the memory and then check the others. And then check, before this gets added to the stack, check if it's already in there. Okay, so I think what we should do actually is add it to the memory here. So as soon as you get there, but point and direction doesn't exist. So instead say if row, column, current direction is in, so, well, we've been here, which means it's possible. So essentially we just want to say min score at point of row, column, current direction should be equal to score. And then we only update it. So if we're here, then it means okay, so let's leave that there. So for now, we'll just set it equal to the score. So this would set it to 0. And then when we get here, it would set it to 1000. But it's making sure that, okay, so if it's, so the condition that we don't want to add it to the stack is if that point and direction is in it and so I guess we could say before we add it to the stack. So right here. Yeah, we could just do right before it, we could filter it out. Because we do need to calculate the new score of what it would be to get there. And min score at points of point and direction. So what we've already seen is less than my score, then you just pass. And you don't do it. Okay, so let's see what happens where it fails. +1. Okay, that's actually a good error to have. That's something I forgot to do. So if obviously you're going to go out of bounds. So I don't use I anywhere in this function, right? So I could just say I equals direction index +1 mod 4. And then -1. Okay, so does it go through the whole thing? So let's print min score at point. Okay, so this gives us every point. Okay, first of all, why does it look like that? Why is it like a... Oh, because direction is a tuple itself. Okay, so this is at... It's telling me at position 12, 1. So 12, 1 right here. The minimum score when you're facing left is 1001. All right, so let's print. So instead of printing the whole thing, let's print. I could say like 4 direction. In this, so we don't care like what direction we're visiting east from. If, and then do we still have access to end? Yeah, okay, so if end, alright, let's say, alright, if end row and column direction in min score at points print. So if it's in there, then print the score. Like that. So you're telling me it's never visited? So you're telling me 113 is never in the array. So 113. Okay, so we know that 12-1 is in there. So let me just make sure. So the direction. Okay, so this should be in there because I just saw it. Okay, so there's 2 ways. So I'll just say test row, test column. Just for a little debugging here. So test row, test column with direction with score equals this. Okay, so 12-1 with direction up and direction down. So how do we ever get to 12-1 with direction down? Unless row 12 is this row right here. So I don't know how we got there from direction down. All right, let's so if I had to guess, it explores these first. Let's just print, maybe print currents. And just see what it's printing, like what order it's exploring it in, and then that will help us. Okay. So current is 13.1. And let me just grab the test input. Still not muted. Nice. Okay, 13.1. Oops, sorry about that. 13.1. 12 ones. Okay, so my question is why is it not exploring the other ones first of all? So it should explore the ones to the east. Okay, let me restart. So forward, the point ahead is 213. And it's not a wall. It is a dot. It's not that. So yep, it's forward. And it's not in min score visited, so we append it to the stack. Oh, because I'm doing... I suppose it doesn't really matter. That's because it's depth first search. So I don't think it really matters. So where's stack? Okay, so now we're gonna pop the one where we went counterclockwise. That makes sense. Okay, so that's why we got that. Okay, so knowing that the only one now should be 11.1. Yep. So then it will also go to 10.1. Okay, it went to 11.2. Okay, I'm gonna do it with a BFS because that's just how I was tracing it in my head. Dick. I keep doing that. There we go. So say instead Q equals deck with this stuff in it. Okay, and then we'll say while Q. So we'll pop from the right. I don't say pop right? Yeah. And then just when we add it, Q dot append left. Okay, so now this should be more what I'm expecting with the print order. 13 one. That's the start. So now it should go, it'll add both of them to the stack. Now it goes 13 2. Okay, and now it'll go 13 3. Wait. Why didn't it do 13 3? Is it in the stack? Or the queue? No. Okay, so it never got added to the queue. Okay, so let's see. I think that's indicative of some problems. All right. So current direction, or I guess new direction, is to the right. So to the right is not a wall. It is that, and it's forward, so it'll outscore, and it's not endpoint direction. So now we'll append left. The one to the, yeah, okay. Okay, so now it's clockwise. So clockwise is a wall. Okay, now it's counterclockwise. So this is a period, so it'll add 1,000. That's not in there yet, so we'll append it to the queue. Okay. And now that's it. So we popped. Okay, now so that was that. And now we're back at the queue. So current, make sure I'm still not muted. Okay, still not muted. So current equals queue.pop. So we pop 12 1. No, where's current? Yeah, we popped 13 2. Yeah, perfect. Okay. So current is 13 2. And now we're checking forward, and then so new direction. Oh, wait. No, that's fine. Okay. 13 3. So 13 3 is not a wall. It is a dot, and it's forward. Oh, I see. Okay. So to be honest, I don't know why it's not working. It seems to be working. So this happened to me last episode where it was working and I doubted that it was working. So I'm just gonna keep printing stuff until I see something that doesn't make sense. What's the file called again? Reindeer maze. Okay, so 12 1 is in it. Okay, so 12 1 is in it. So let's check. So that's 12 1. So let's check 11 0 1 2 3 4 5 6 7. Okay, 11 7. Back to my code. Okay, so 11 sevens in there. Let's check. Oh, it's because it's an E. Okay, I'm off by 3 points. How did I get that? Okay, for a debugging tool, I'm going to say step count, and then every time. Oh, because. Oh. Was it because I'm turning and stepping? Is that the problem? So, should I do that? So now I'm over. Okay, I think it has something to do with this. So if we just go forward, it's 1 point. If we turn to the right, we have to turn and go forward. And I'm doing that both in one turn. But now it's 70-40. I'm close, so it might just be something. One tile at a time, but they can never into a wall. They can also rotate. I don't think this will do anything, but. $740, yeah. I'm missing something. So here, there are many paths, but taking any of the best paths would curve a score. Could it be like when I'm doing E? E should be right ahead. So maybe if I manually calculate it, so if I get to this point here, 1, 2, 3, 4. So this point should be 1,000, 1, 2, 3, 4. So this point here should be 1,004. So that's row 9, column 1. Okay, so row 9, column 1. Row 9, column 1, and we're expecting 1,004. Okay, I have 1,005. That's good. We have an error. So let's. So this point here is row 12, column 1. Wait. Yeah, 0, 1, column 1. Row 12, column 1. And I'm expecting it to be 1,001. Okay, so it's 1,002. What about row 12, row 13, column 1? Row 13, column 1. So I'm expecting this. This is a start position, so it should be 0. Okay. But all of a sudden, when I go up 1 row, it goes up. And 5,015. So that would be 1. So it would be 1, 2, turn twice, 3, 4, turn once, 5. So that actually looks right. 1, 2, 3, 4, 5. And I'll say, or if it equals S. Okay, that doesn't fix anything. Okay, so let's look at the code why that's happening. So we're up by 1 point for no reason when it should be okay, so current is 0. That's good. Okay, so now forward is gonna work. Let's just let me try something. So if I make this here, does it still, whoops. So if I try this input instead, it's 101 now. Okay, so something about if you checked forward, Okay, so if this is a dot, now it's 102. Okay, well that's useful. So maybe we have to undo these score changes when we append the new one. It seems. Okay, what about this? Nope. Huh, okay. Let's trace it here. It's gonna take a little bit, but that's okay. This is the problem. Still not muted, looking good. All right, so score is 0. We're gonna look at forward, get our directions. It's not a wall. Okay, so now, I don't know what this watch thing is. I'm gonna bring it down. Okay, so if it's a dot, which it is, direction is straight, so we're gonna add 1 to the score. Now reset score every time, right? Yep, okay. So we're gonna add 1 to score. So score is 1. So it's not in min score. So we're gonna skip this. And now we're going to append the new score. Oh. So here the 1 saves over. Okay, so now when this works, it's going to be 1001. So this has to reset to starting. Okay, so we're going to say starting score. Like that. And then here we'll say score equals 0. And then when we do this, we'll say starting score plus score and starting score plus score. Like that. Shoot. Okay. So let's see if that gives us the answer we're looking for. Okay, perfect, it does. So let's try the other example. Here's a second example. So let's try this one. 11048. Okay, now let's try our puzzle input. So this is probably going to take a long time. Okay, so get rid of test input here, guys. This is exciting. This is a hard one. And yeah, we're not going to print anything while we do this giant problem. So if you guys don't know, printing actually takes a very long time. Oh, well, we have to print something. So we'll just print at the very end. And I'm not printing anything else, right? Okay, cool. Okay, so it's taking a really long time. I hope we don't have any infinite loops. I could also use the distance trick on which one it searches first. I didn't print the thing that I wanted to print. Okay, so I get it from all four directions. Does that make sense? No, not at all. It should only be coming from up. Oh, four direction. Well, yeah, that makes sense actually. Okay. So if it's in it, then we want to print min score at point for that key there. All right. So a couple things I can do. So I could do the 1000 trick because that will reduce the runtime by a quarter, I think, or maybe even more, probably by a lot, because then we just won't. We could trim those out a lot faster. This might be my last day doing Advent of Code because these problems are getting kind of hard for me. So I think this definitely involves some dynamic programming, which I haven't even really done the basics of yet. Well, I have in the past, but okay, let's see that. I have in the past, but I want to get more familiar with it. That's not the right answer. Your answer is too high. So maybe we found a path, but it's not the... It is the only way we were able to reach E, though. So... Yeah, I might leave this one unfinished. I think this was a really good exercise and a good signal to me that Advent of Code might be getting a little too complex for me. I mean, I don't think this problem's that hard. It just requires some fundamentals with traversing and keeping track of states. So I want to go hit the basics of that before I come back. So for day 7 here, we're going to leave the problem unfinished, but that's fine. In my books, I think it was a good. It was a good exercise. Got a lot of coding done. Yeah, I think I'm definitely getting a lot better, even though I didn't solve this one. I'm sure I'm not that far off, but yeah. So tomorrow I'll do some neat code. So I'm going through this like roadmap and stuff. So right now I'm doing linked lists and trees. I'm hoping to complete the whole thing. So tomorrow I will do a linked list problem. And just put admin code on pause for now, and then maybe I'll revisit it. But yeah, so that's the episode for today. Anyone watches this has any suggestion on why I'm not finding the lowest path? I'm guessing what my solution found was a valid path, but maybe not the lowest. So yeah, that's it for today. Thanks for watching, and I'll be back tomorrow.